Hi everybody. In this section, we're going to keep going in chapter 6 and we're going to do hyperbolic functions. So a lot of you guys probably haven't seen this before, so there's a bit of algebra review. If you have seen it before, great. If you haven't, you'll learn everything you need to know in this section. So the idea here is that we're just going to look at even and odd combinations of e to the x and e to the minus x. And it turns out that this pops up so much, just naturally in applications, that they're given special names. And they have a lot of similarities to the ordinary trig functions. And it turns out that the relationship between these functions is the same relationship to a hyperbola that the trig functions have to the circle. So here's the first function we're going to look at. It's called the hyperbolic sine function. And if you're pronouncing this out loud, you just call it sinh. It's just the way it's pronounced. So this is sinh x. So look at what it is. It's half of the difference between e to the x and e to the minus x, right? And it's called the hyperbolic sine function. Domain and range, negative infinity to infinity. You can see that because it has e to the x and e to the minus x. Both of these are 0 to infinity, but because you're subtracting, you get the negative portion as well. Here's another one called the hyperbolic cosine function. So it's that magenta one there. You just pronounce it cosh. So sinh and cosh. And it's just the average of e to the x and e to the minus x. So they're kind of weird functions, right? There's nothing quite like them that we've seen yet, but it turns out they pop up absolutely all the time in applications. So, quick trig review, right? So when we're doing sine and cosine as points on the unit circle, you can write it as y equals sine t and x equals cosine t. That's called a parametrization or parameterization. And essentially, t is just the angle. So you could call it theta if you wanted, but the idea is that t is just general, because t can go around and around, right? And so if we're on the unit circle, then cosine squared t plus sine squared t equals 1 for all values at t, right? And you learned this in trig. You called t theta, but this is just, again, a general formula. So on the unit circle, t is this angle, right? And it turns out the measure of this angle is double the area of this sector. So we saw that a little bit earlier, right? So again, the angle is double the area, right? So if you think about the unit circle, its area is pi, right? Because it's pi r squared with a radius of 1, and the angle is 2 pi. So it's based on that. And when the angle is 0, the area is 0. And it's linear, right? As you add more angle, you put on a proportional amount of area. So I'm not proving that geometric property. Just take that as a given. So it turns out that this hyperbolic sine and cosine have the same relationship to the unit hyperbola x squared minus y squared equals 1. And so basically, it should follow that cosh squared t minus sinh squared t is 1. And so here's the proof down here, right? So you just plug in the definitions, square everything. All right, so I factored out the 1/2. Square everything. So you've just squared or FOIL everything out. It turns out everything cancels except the 2's. Right, so you get 2 minus negative 2 is 4, and 1/4 of 4 is 1. And on the unit hyperbola, t is not an angle, at least not any way that we know how to measure it, but it still is twice the area of the shaded hyperbolic sector. So if you're on the unit hyperbola and you want to know the area of a sector, you can just work backwards and compute t for any point on the hyperbola. But it's not an angle. It's something like an angle, but we're not getting into the geometry of it. So what we can do is we can use what we know about trig functions to create new hyperbolic functions. So all we have to do is just arrange sinh and cosh in different ways and see what happens. Just create different things. So this is pronounced tanch. It's just sinh over cosh. And I went ahead and did the algebra for you. It simplifies to e to the 2x minus 1 over e to the 2x plus 1. And you get this cool little graph, right? So it sort of looks like arctan, right? It's just that divided by that. And here's some more. Coth, sech, and this is just hyperbolic cosecant. There's no like short way to pronounce that. And the definitions are the same as the trig definitions, but obviously its representation is different because we're not doing trig functions here. These are hyperbolic functions. But again, analogously, they correspond to a lot of the things we've seen before. And here's just a summary of the domains and ranges of all of the hyperbolic functions. All these follow from their definitions. In fact, you have some homework problems, and we're going to see some here in a second, where you explore the limits of these things so you can see the domain and ranges. And we can develop other identity formulas, starting with the fundamental hyperbolic function identity. So this is sort of the analog of the Pythagorean identity that you get for circles, but it's just called the fundamental hyperbolic function identity. And just do some algebra, and you see that here, if we divide through by cosh squared, this becomes 1, this becomes tanch, right? And this becomes sech. So you get another identity that looks really similar to one you might have seen in trig. So we're not going to work on identities. We're not doing any of the algebra properties here in a calculus class. The only algebra stuff we're going to look at is limits, which is still sort of like a calculus thing, and we're going to look at inverses. But we need inverses because we need to prove some of the formulas that we're going to see. So let's just do a little bit of work with hyperbolic functions just to see how we solve, like, what does this stuff mean? So, all right, so here we go. So we have cosh x is 25/24. Right, so that means, e to the x plus e to the negative x over 2 is 25/24. How do we find this other stuff? So we're going to start by just using the fundamental hyperbolic identity. Once we find this, we'll be able to find this and this. And this is the way you should do it on the homework too. You have stuff like this on the homework. This is the way you should do it. So there's our fundamental identity. Plug in what we know. We know cosh squared. So we know cosh is 25/24. So we square it. So this squared is 625 over 576. So this, all I did is swap sides and subtract. So sinh squared is 49 over 576. Take the square root. You can assume that these are all positive. It's not like when you're doing trig functions where you have to keep track of the angle and which quadrant you're in. This isn't quite like that. You're never going to have to do negative values for these. We're just assuming everything's in the first quadrant. So there you go. It's 7/24, right? It's easy to check your answer, right? So, square this, subtract this, and you get 1. Works out real nice. Now, what about hyperbolic tangent? What about tanch? Well, we already know. We just found sinh x. We found cosh. Just plug in what we know, and some easy arithmetic gives you 7/25. Again, be careful not to write these as decimals. The homework will not accept decimals. Now, what about hyperbolic secant? Well, that's just 1 over cosh. So that's just 1 over 25/24, which is 24/25. So all the problems on the homework that look like this, you're going to do in a similar manner. If you're given hyperbolic sine or cosine, find the other one right away. And then all of the other all of the other hyperbolic functions will follow directly from there. All right, let's keep going. So let's look at some limits now. So this is just if we were proving the domain and ranges. So the domains of these things is negative infinity to infinity for all of these. But here we're like proving the ranges, right? You look at as x goes to infinity or negative infinity. Here I just picked infinity for all these just to make the arithmetic easier. So if we want to find the limit of sinh x as x goes to infinity, just plug in the definition. Well, this is infinity, right? E to the infinity power is infinity. So this is going to be infinity, and this is going to be 0, right? E to the minus infinity is 0. So you just get infinity minus 1/2 of 0, which is still infinity. So nothing too fancy going on there. Again, it follows from the domain and range. So it's easy to verify. Or you can check your work with a graph or a table. What about tanh x? Well, I'm going to use the definition again, right? Now here, I'm not allowed to plug in infinity, because that would just give me infinity divided by infinity, which we don't know what that is, right? That's indeterminate. So instead, I'm going to multiply numerator denominator by e to the minus 2x. Now I can bring those limits in. I'm not showing that, right? 2 days left in the class, I'm not showing that, right? Just evaluate everything separately, and you get 1. So this is really the only way to do that. You're not allowed to say e to the 2x, you know, or you might like try to divide through by the highest power in the denominator. That's fine, but that's the same as doing this, okay? So those are equivalent. Because the highest power in the denominator is e to the 2x. So if you divide by that, that's the same as multiplying by e to the minus 2x. I like doing it this way because then you don't have fractions stacked on top of fractions. So it's a little cleaner and easier to follow. Last one, sinh x divided by e to the x. So we have to do some preliminary algebra here. So I put in the definition of sinh x, put it over e to the x, and then I simplified. Now I just compute this limit separately. So 1/2 stays 1/2. This becomes 0 again, so it's just 1/2 minus 1/2 times 0, which is 1/2. So not too hard. This whole section is really just based on properties of e to the x and e to the minus x. All right, so a couple applications. The most common application is the shape of a hanging wire. If a heavy flexible cable is suspended between 2 points at the same height, it takes the shape of a curve called a catenary. And the equation is given on the homework, as you will see. Here's another one. This is the Gateway Arch in St. Louis. It actually has this equation. So the fellow that designed this did some math, and he figured out that this is the strongest, most stable shape for an object with no supports other than just at the edges. And you also have a homework problem on this. So more about those when you get to the homework. I'm not going to do anything else with those. The problems are not difficult. Let's get into the calculus. Oh, even a non-hyperbolic functions. So this is just to follow up with stuff we did earlier in the class. And this is going to help us with derivatives, right? So remember, the derivative of an even function is odd, the derivative of an odd function is even. And you can see that the derivatives look a lot like the derivatives of trig functions. The only difference is that it doesn't follow the rule of all the co-functions are negative, right? Because well, these aren't trig functions, so that only works for trig functions. So the derivative of cosh is sinh. So this follows. And this one, so derivative here, you still get hyperbolic secant squared. But the derivative of this is negative secant tangent. So it's a lot of the same stuff. So if you looked at a list of trig functions and a list of hyperbolic functions, a lot of similarities, but not the same. So let's go ahead and prove this. It's a real easy proof. It's the only one I'm going to prove. The rest of these are very similar, so I'm just going to prove the first one so you know that it's believable. So I'm just going to plug in the definition. It's going to evaluate the derivative. Don't forget your chain rule on the e to the minus x. Remember, you don't need a chain rule on e to the x, but you need a chain rule on e to the minus x. So that just becomes a -1, which flips the sign, which is cosh x. So pretty easy proof. Make sure you can do the proofs of all of these, because they could be on the exam. But I'm only going over this one, so make sure you can do them. All right, next one. Let's so more about derivatives. So any of the differentiation rules can be combined with the chain rule. Obviously, that's always true. So let's see how this works. So let's find the derivative of sinh squared of x. First thing you do is you write sinh squared in its expanded form so we can use the chain rule, right? So just this here is just a more condensed way of writing that. So just take the derivative and rewrite it so it makes sense. So it's 2 sinh x, drop the power by 1, times the derivative, which is cosh x. Now you might be tempted to stay here. And this is correct, but there is actually a more compact way to write this. Replace sinh and cosh with their definitions, distribute everything, and you end up with this. Distribute the 2, and this is just sinh of 2x. So this is actually a much more condensed way of writing this. And what we ended up doing is proving another identity. We've proved that this is equal to that. And that stuff happens a lot with hyperbolic functions, just like trig functions. There's a lot of identities. So we're not proving a bunch of identities. I just wanted to show you that if you're doing the homework and you're checking your answer against the answer in the book and you're like, what's going on here? It's because you probably haven't simplified enough. On an exam, staying here would be fine. The homework might want you to simplify all the way. So just watch for that. Okay, so we're going to look at the integrals here of the hyperbolic functions. Obviously, these follow directly from their definitions. I'm not going over the other integral formulas. You guys know how to read derivative formulas. Derivative formulas automatically give you the integral formulas. And now I want to talk about inverse hyperbolic functions. So since the hyperbolic functions are defined in terms of exponential functions, it makes sense that the inverse hyperbolic functions can be expressed in terms of natural logs. And it turns out they can. So here's the first 3. Here's the next 3. Here's the domain and range of all of your inverse hyperbolic functions. I want to point out something that a lot of people miss, and that is look at the domains and ranges of, where is it? Here it is. Hyperbolic tangent and hyperbolic cotangent. They don't overlap. The domains do not overlap at all. That's really important. And we're going to see it a little bit later why it's important. Yeah, these domains do not overlap at all. Which means you could graph them together on the same set of axes and they wouldn't overlap. It would still be a function, right? Because the range is -infinity to infinity. So that's important. All the other ones overlap at least somewhat, like inverse hyperbolic cosine and inverse hyperbolic secant overlap at the point 1 on the domain. And they have the same range. And so on and so forth. All right, let's do a proof. So we're going to prove the first formula. Where is it? Right here. We're going to prove inverse sinh, or arc sinh, or inverse hyperbolic sine, whatever you want to call it, is ln of x plus square root of x squared plus 1. Right here. All right, so first thing we're going to do is going to write y is sinh x. Remember, we're trying to find the inverse, right? So we're going to use that inverse. So write it using the definition. Then you switch x and y. So I'm annotating the algebra steps here because, as you can see, this thing's going to have a bunch of algebra steps. So switch x and y, and now we want to solve for y. So what I'm going to do, and this might seem weird, I'm actually going to multiply both sides by 2e to the y. You're not going to know why I'm doing that right now, but you will. Because the problem here is I have an e to the y and an e to the minus y. There's no algebra in the world that can factor both of these out, okay? But we do have algebra that will allow me to factor this if I multiply by 2e to the y. So that's what we're doing. Then I'm going to replace e to the y with u. So it's like a u substitution. I could use any letter. I could have used t, but think of it like a u substitution, even though we're not doing any derivatives. So here, u squared is e to the 2y, right? E to the y squared is e to the 2y. Negative 1 stays negative 1, and 2x e to the y becomes 2x u. Now I'm pulling everything to the left. So I'm just subtracting 2xu from both sides. And what you might notice is that this is a quadratic equation in u. Remember, like ax squared plus bx plus c equals 0? Here, except instead of x, we use u. So a is 1, b is negative 2x, c is negative 1. So because we have a quadratic equation, we solve for u by completing the square or using the quadratic formula. I did completing the square. You guys could use the quadratic formula. So completing the square, you bring the 1 to the right side, divide this by 2, divide the coefficient by 2 and square it, so you get x squared. And then you add x squared to both sides. Factor the left side, that's just u minus x squared. Take the square root, and you get u equals x plus square root of 1 minus x squared. So one thing I want to point out, some of you are thinking, why isn't this plus or minus? Well, what we saw earlier was that whenever you're doing hyperbolic sign or inverse hyperbolic sign, you're allowed to pick either positive or negative when you take square roots. In this case, we're just picking the positive part. It could be negative, but you can't pick both because it won't be a function when you take the inverse. So that whole thing was completing the square. Again, if you did quadratic formula, you'd get a plus or minus here. You just can't keep both of the plus and minus or it's not an inverse. You have to pick one or the other. Then you back substitute e to the y in and take natural log of both sides, and you're done. If you guys took college algebra in high school or here at LCCC, this problem actually was in the college algebra, the Math 171. So this is actually, it wasn't called hyperbolic sign. It was just find the inverse of this. So some of you guys might have seen this before. Moving on. Now, the derivatives of the inverse hyperbolic functions. Oh man, there's a bunch of derivatives, right? I'm not going to prove all these. Right, I'm just going to prove hyperbolic arc, hyperbolic sign. And then the other proofs are similar. And before we prove this formula, we need to prove another identity formula. So if you have cosh squared minus sinh squared is 1, that's our fundamental hyperbolic identity. Add sinh squared to both sides and take the square root. Again, choose the positive value. It's not plus or minus. These aren't numbers. These are functions. You have to choose plus or minus. So that is our new identity. We're going to use that identity in the proof. All right, so if y equals inverse hyperbolic sign of x, then hyperbolic sign of y equals x. And we're going to use implicit differentiation. This is the same technique we used earlier when we did the derivative of inverse sine, right? It's the exact same technique. So when you take the derivative of both sides, we know the derivative of this is cosh y, but it's cosh y prime. Over here, derivative of x is just 1. And then solve for y prime, which is 1 over cosh y. Previous slide, we showed cosh y as square root of 1 plus sinh y squared. And sinh y squared, sinh y is x, so sinh y squared is x squared. And we're done. So real easy proof. Make sure you can do the proofs of all of these, because they could be on a test. And of course, these can all be combined with the chain rule. Right, so you guys are used to seeing that by now. Which also leads to use substitution if you're doing integrals. So you don't have hardly any integrals on the homework. It's mostly just derivatives. All right, so let's do derivatives using inverse hyperbolic functions. Last example, let's find the derivative of inverse hyperbolic tangent of sine of x. So just take the derivative of both sides with respect to x. On the right side, you get 1 over 1 minus u squared, so u is the inside function, times u prime. So sine of x prime is just cosine of x, and 1 over sine squared of x. And you guys might be tempted to stop here, right? But you can't stop here. We're not done. Even though if you type this in Wolfram Alpha, it tells you to stop here, you can't stop here, because 1 over sine squared of x is cosine squared, and that's secant x. So this is considered unsimplified. Right? So we have the derivative of this strange thing is secant x. And this should seem strange because we proved in section 6.2 that the derivative of this is secant x, right? The integral of this is that. And this is telling us the integral of secant x is this, is inverse hyperbolic tangent of sine x. So that's pretty weird. So I want you to think about the answer to this question, because it could be on the exam. Does our result from example 6 prove that those two functions are equal and they could be off by a constant? But are those the same function? I'll let you think about that. Try to prove it on your own. If it pops up on the exam, you'll get it right. Well, that's it. One more section to go, guys, in the next video. And as always, if you have any questions, email me or post on the discussion forum. And until next video, have a good day, and I'll see you guys later.